11.7 Areas and volumes of similar solids. We've dealt with similar figures before, and we said that similar figures, the angles are congruent and your sides are proportional. That means that we use ratios. We compare those ratios using a proportion. We are going to use a ratio to compare our areas and volumes. All right, some definitions here, some vocabulary. Similar solids have the same shape. That's going to be talking about our angles, right? Same shape. And all, that's important, their corresponding dimensions are proportional. This is going to be like our sides. And of course, the corresponding linear dimensions, this means length, are related by a scale factor. Now, some important things to remember here. Any two cubes are similar, just like any two spheres are similar. We've talked about circles. All circles are similar, and their radii are going to give you the scale factor. Cubes are going to be the same way. We've discussed this with equilateral triangles as well. Let's look at our first problem here. Are the two rectangular prisms similar? If so, what is the scale factor of the first figure to the second figure? So we'll label this one number 1 and this one number 2. First figure to the second figure. Remember, it doesn't matter which way the scale factor goes unless it is designated. So we look at our two figures here, and we have sides of 3, 3, and 2 on figure 1, and 6, 6, and 4 on figure 2. So now we don't have any distinguishing features to tell us which sides are proportional to each other, but you can kind of tell. Your larger side is going to be proportional to your larger side. So let's check that here. We have a 3 to 6, which is a 1/2. And we have another 3 to 6, which reduces to a 1 to 2 ratio. And we have a 2 to 4 ratio, which again reduces to a 1 to 2 ratio. So all of our sides are proportional, right? They have the same ratio, a 1 to 2 ratio, which tells us that our scale is a 1 to 2 ratio. They are similar because your corresponding linear dimensions, that is just talking about your sides. Your corresponding linear dimensions, all of our sides, our corresponding sides, are proportional. And we calculated our scale factor. Let's look at the next one. We have a 2 and a 3 and a 2 and a 3 and a 6 and a 3. So let's check these. I'm going to say the 2's and the 3, 2 to 3, this one and this one. Okay, that's just 2 to 3. And we have another 2 to 3, so things are looking good. This one and this one. All right. 3 to 6, that reduces to not 2 to 3, that reduces to a 1 to 2. These prisms are not similar because your corresponding linear dimensions are not proportional. We were doing all right there for a while, but all of your sides, corresponding sides, have to be proportional. Pause the video and do the next problem. All right, this one was pretty easy. We wanted to know if the two cylinders are similar. So we know that we need to compare corresponding linear dimensions, corresponding sides, corresponding lengths. In this case, we have cylinders. The important part of circles, is the radius. So we are going to compare our radii, and we are asked to compare the first figure to the second. So I have a 6:5 ratio, and then I'm also going to compare their heights, and I have a 12:10 ratio, which reduces to a nice 6:5 ratio. So yes, they are similar, and our scale factor is 6:5 for figure 1 to figure 2. So just a good review there of what we've done before. All right, let's look at our next example. We have two similar prisms, okay? And we have if we look at our sides are going to be proportional. We have a 2:4 and a 1:2 and a 3:6. All of those are going to be a 1:2 ratio. So we have a scale is 1:2. And then that also tells us that our side lengths are 1:2. And we learned previously that our area ratio is our scale squared, right? Or our perimeter, our length ratio squared. So if we look at our surface areas, our surface area ratio here, surface area of 1:2, is 22:88, which gives us a 1:4 ratio, just as we expected. So what do you expect of the volume ratio? Well, length is just length, area is squared. So what do you suppose of volume? Volume is going to be our scale, oops, that's a 2, our scale, you guessed it, cubed. So that's going to be a 1:8 ratio. Okay, volume is a 6:48 ratio. If we reduce 6 and 48, we get a 1:8 ratio. So some important things to remember here. Area, surface area, is the square of our scale factor. Your volume ratio is the cube of the scale factor. And this applies to all similar solids. Now, this makes our theorem here. If our scale factor is A to B, or A to B, they're more useful to us written in fraction form, then the ratio of corresponding areas, your area ratio is A squared to B squared. Let's write this better up here. This is scale, is A to B. And we could also remember that our perimeter ratio is also A to B. That came from the last time we did this. And the ratio of your volumes, your volume ratio is A cubed to B cubed. So this is easy to remember. You have a scale. Scale just compares lengths. Perimeter is also a length, so perimeter is the same ratio as your scale. Area is always squared, so your area ratio is your length squared. And volume is always cubed, so your volume ratio is going to be your lengths cubed. All right, let's look at an example. We want to find the scale factor. We are told that the square prisms are similar, and we want the scale factor of the smaller prism to the larger prism. Okay, what are we given? We are given volumes. So we know that our volume ratio is 729 to 1331. Okay, Now, we know that that is a cubed over b cubed. How do we get rid of a cubed? Well, how did we get rid of square root or squared? We square rooted. So how do we get rid of cube? We cube root. And don't forget on your calculator, cube root is up hat. Don't forget your parentheses, 1 divided by 3, or your math button, number 4, and it gives you the actual cube root symbol. Don't forget your parentheses in there as well. Okay, so lucky for us, these are perfect cubes. And so we get a scale factor of 9 to 11. Perfect cubes aren't as easy to see, but your calculator will know what they are. All right, pause the video, do the next problem. Okay, we want to find out what is the scale factor of two similar prisms. Okay, so we know they're similar. And they have surface areas of 144 meters squared and 324 meters squared. So I know that I have an area ratio of 144 to 324. I know that area is squared. So to get my scale factor, I'm going to square root both of those. I recognize 144 as a perfect square. And 324 happens to also be a perfect square. I get 12 over 18. I can reduce those to 2 to 3. So my scale factor is a 2 to 3 ratio. Now from here, I can also find my perimeter ratio. Perimeter would be a 2 to 3 ratio. And what would volume be? Volume would be cubed. 2 cubed over 3 cubed would be an 8 to 27 ratio. All right, part B is, are any two square prisms similar? Now you really want to say yes on this one because you see the word square, but on a square prism, square only refers to the base. So this is a maybe. It's a sometimes. If your heights are proportional to the proportional of your squares, the sides of your bases, then yes, they would be similar. But your heights may not be proportional. So that is a maybe. All right, let's look at our next example. Using scale factors. Oh, we're painting. The lateral areas, okay, that's an important word right there. Lateral areas of two similar paint cans are given. So we know we have lateral area. And the volume of the smaller can is given. We want the volume of the larger can. Well, when we're doing stuff like this, you always need to get to your scale factor before you can go anywhere else. So we find our scale factor using our area ratios. We know that our areas are, we know our area ratio, and then area is always squared, so we square root those. Now these are not perfect squares. So we could either simplify our radicals, or we're going to use them again to find the volume. We write a proportion. Volume of the large over volume of the small is our scale factor, which is right here. We know our scale, right? And we've left it in radical form, which is just fine. But we have to cube that. So we are cubing the square root. Okay? Your calculator will do that. Make sure that you use your parentheses. And we substitute in, we know the volume of the small can. And then we simply cross multiply and solve for the volume of the large. your calculator can easily do the cubes of these square roots. Just be careful with your parentheses. We should write good example here. This deserves a lot of stars. If you have trouble with squares and square roots and cubes, good example. This would be a good example for you to follow. Good example all around. All right. Pause your video and try this example. All right. This one is pretty straightforward, but it can feel a little challenging. We are given a volume ratio and one surface area and asked to find the other surface area. So the first thing we need to do is find our scale. We're given our volume ratio, 128 to 250. We know that volume is cubed, so our scale factor is going to be the cube root of our volumes. Now, neither one of those is a nice cube root, so we're just going to leave them as they are. Now we know our area ratio is our scale factor squared. So I can write a proportion, area small over area large, equals my scale factor squared. So I simply substitute in my area small over the 250. I'm told the area of the larger solid is 250. And then I put my scale factor in. And notice here that I have used my parentheses and squared both of these. Now you can put them in your calculator just like that. Or, if you remember back in our last lesson, we said that roots are a fractional exponent, so this is raised to the 2 power times the 1/3 power. So you can also use the 2/3 power and get the same answer. So whichever one you're more comfortable with works just fine. Both of them do the same thing. So to get our area small by itself, we simply multiply both sides by 250, put it all into our calculator. Be careful when you're multiplying these. Use your parentheses. Calculator follows order of operations. And we come out with 159.575, so the area of our smaller figure is 159.6 meters squared. All right, that was very good. All right, our last example of chapter 11 here. You can compare capacities. Capacity is just a volume and weights of similar objects. Weight is going to be similar to a volume as well. Weight is just mass, and mass just takes up space. So the capacity of an object is the amount of fluid that the object can hold. Capacities and weights of similar objects made of the same material. Okay, you probably learned about this stuff in science. So your capacities and weights will be proportional to their volumes. So let's think about this. Let's look at our example here. It says a bottle that is 10 inches high holds 34 ounces of milk. The sandwich shop in the picture is shaped like a milk bottle. To the nearest thousandth ounce, how much milk could the building hold? Well, we already believe it's going to be a lot. We're told that our scale factor is 1 to 48. So that's a good place to start. So because we know that capacity is a ratio of the volumes, we know that volume is cubed. So we are going to find our volume ratio, which is our scale cubed, 1 cubed to 48 cubed, and we get 1 to 110,592. We use this to write our proportion. Okay, we know that our small bottle here on top to our large pretend bottle over there Okay, and we were told up here that our small bottle that is 10 inches high holds 34 ounces of milk. So our volume is 34 ounces. That goes on top. We want to know the volume of our large milk bottle over here. That's on the bottom. We simply cross multiply and solve for x. So this is our volume of our large milk bottle. Our capacity of our large milk bottle is about 3.7 million ounces. That's a lot of ounces of milk. All right, so these work the same way we've been doing all the other problems. Just a few little bit different wording. Go ahead and give our last problem here a try. Okay, we're told that we have a marble paperweight shaped like a pyramid. That really doesn't matter, but it gives us something to visualize. And that paperweight weighs 0.15 pounds, so not very heavy. We want to know how much does a similarly shaped paperweight weigh if each dimension is 3 times as large. When we're talking about dimensions, we are talking about scale. We are talking about length. If each length is 3 times as large, that tells us that our scale is a 1-to-3 scale. Well, we know that weight follows a volume ratio. So we know that our weight ratio is cubed, a cubed over b cubed. So we get a 1-to-9 ratio for our weight. Then we are going to use that to write a proportion. Okay, right here we write our proportion. And I'm putting small over large, so I make a note of that. I use my 1/9 that I know is my weight ratio, and then the weight of my small over the weight of my large. And then I simply just cross multiply, and we find out the weight of the large is 1.35 pounds, so quite a bit more. So not overly difficult. You just have to be careful and do each step. So our steps are here. This is good information to have. Number 1, you always have to find the scale. Okay, everything comes from scale. No matter what you're given at the beginning, you need to get to scale if you're not already there. If you're given an area ratio, you square root, and you know where the square root button is on your calculator, or you can use the up hat 1/2. Don't forget your parentheses. If you're given the volume ratio, you need to cube root, and the cube root button is under the math button, number 4, or you can use the up hat to the 1/3 power. Don't forget your parentheses there as well. So then that will give you your scale. Once you have your scale, you find the new ratio that you want. So if it's an area ratio that we're looking for, we square the scale. If it's a volume ratio we're looking for, we cube the scale. So figure out which one of those you're looking for. And then we use that value to write a proportion. Okay, and make sure that you label it if it's small to large, or figure 1 to figure 2, or if it's large to small. Okay, but that will help you. And then your known ratio goes in here, and you're comparing it to what you're given and what you want. So again, these are a little more complicated. Roots can be a little bit confusing, but once you use them, you'll do just fine. Try to get used to using the exponents for roots. Your life will be much easier if you do that, especially in future math. And label everything. Again, these problems are not difficult, but they are complex. So do them one step at a time, and you will do very well.